Hi, everybody. I hope your exam went well. We're getting into chapter 2 now, and we're looking at general triangles other than right triangles, which was all about chapter 1. So, oblique triangles are triangles that are not right triangles, and there are two types. They can be acute and obtuse. Acute have all acute angles less than 90 degrees, and obtuse can have one obtuse angle. In this chapter, we're going to be looking at these four cases and how to solve a triangle, which is pretty interesting that you can solve triangles that are not right and very important when you get into surveying. And actually, we might have an optional class where you guys can actually help the surveying class at Columbia College and determine the area of the lake. So stay tuned for that. So what we're going to look at today is case 1 and case 2, when you have one side that's given in a triangle and two angles, or two sides and the opposite angle. So um, this will make more sense, the law of sines, once I draw a triangle, and this can be any general triangle, okay? So just like what we were doing before, you have a triangle with angles A, B, and C. And the side that's opposite angle A is little a, side that's opposite angle C is little c, and the side that's opposite angle B is little b. So we're going to be using that. And I always want you to draw a picture when you're doing these problems, okay? So the law of sines, it's pretty straightforward. The side of a triangle is proportional to a to the sine of that angle, and that is proportional, I should say, to any other side and its sine of the angle. Okay, so all of these, I'm creating these ratios, and all of these ratios are equivalent. Okay, that's 2.1. Now, with 2.2, we can say the same thing. They just flipped everything, and that's okay to do. So taking the reciprocals, we're going to flip it, and we have sine of A is equal to A, and sine of B is equal to B, and so on. The same goes with if you solve, you can say, okay, A is to B, right here, as sine A is to sine B. This is just going to help you when you're solving these triangles, depending on how you want to set it up. The proof of law of sines goes as follows. These are oblique triangles. One's acute, one's obtuse, so we can consider both cases. We're going to set up the sine of A is equal to h over b. H is just an altitude that you create, so this is my altitude. And using this right triangle right here, you can see H is the opposite angle, B is the hypotenuse. In the obtuse triangle, we're going to use this 180 degrees. This is my right triangle, H is my altitude, and A is my hypotenuse. So I can also say that the sine of 180 degrees minus B is equal to H over A. But what's this right above? What? Are you saying that the sine of 180 minus an angle is equal to the sine of the angle? That's from chapter 1, and we're actually getting to use that now? Yes, that is true. So we can say that the sine of B is equal to h over a. If I take this and I solve for h is equal to B sine A. Sorry for the sloppiness. Now I'm going to substitute this in over here for h, like all the arrows. So now I have that the sine of b is equal to b sine a over a. And if I clean this up and bring the b down here, you guys liking these arrows, or are they confusing you? Sine of big B angle B is equal to the sine of a over A. And a similar case, and you can look in your book, but you can find that the sine of C is also equal to C if you drop an altitude on the other side of the triangle. So one great thing about the law of sines, one result, is that it proves that in any triangle, the largest side is opposite the largest angle. So when we had a right triangle, I just want to take a minute. to point this out. We had two acute angles right here and here, and C was the largest side. That's the hypotenuse. So the hypotenuse was the largest side, and then we had sides A and B as well. So this just shows you that in any triangle it could be obtuse or acute, that and if I said that this was 120 degrees, this side was, let's just make it up, 20 degrees, and this side is 40 degrees, that this side is going to be the longest, which kind of makes sense. The alligator opens its mouth the biggest, so the tip of the mouth right there, that's the length, right? Okay, so the law of sines, and there is a nice little proof in the book. I'm not going to show you that right now, but what I'm going to do is I'm just going to show you a couple of problems from the exercise set. So for the law of sines, we can use anything with case 1 and case 2, one side and two angles given, or two sides and one opposite angle given. I'm just going to make one up for an example. You guys have to do the odds and you can check your answers. That's why I gave them to you. So what I would first recommend doing is, if you're given these parts, we have angle A, B, and C, and I would write in what you're given: 35 degrees, 40 degrees, does not need to be to scale, and side C, which is 12 over here. So in order to do this, you need to find, and it's, if it says solve, we need to find all the missing sides. So find all the missing sides and angles, just like what we were doing before in right triangles. Okay, so we can find angle C because that would equal 180 degrees minus 35 degrees minus 40 degrees. So we have 180 minus 35, which is 145 minus, so that's 105 degrees. We know that side C is 12. So when I set it up, I'm going to use, and I'm going to fill that in, and let me put it in a different color so we know that that's found 105 degrees. So that should add up to 180, which it does. So now what I'm going to do is see that I have that angle C right here now, and the side that corresponds to it. So you have to use that relationship. You have to know both parts. So if I say that the sine of 105 is to 12, as whatever side you want to use now, whatever side you want to find, is you could find B or side A. So let's just do sine of A is to, whoops, which is 35. I'm just going to fill it in. So the book keeps it in general form and then solves it algebraically and then plugs in the numbers. I just like to plug in the numbers. So I say the sine of 35 is to A, and then I solve for A. So if I solve for A, I'm going to bring A over to the top on the left-hand side, and I'm going to bring the other two guys. 12 comes up to the top on the right, sine of 35, and sine of 105 goes down to the bottom. Calculating this number gives me A equals, let's call it that, 7.126. Let's call it that. So here we go, 7.126 for side A. So I'm going to say that's 7.126 for side A. The last side that we have to find is B. So I'm going to do that same thing. I'm going to use this time, and let's just get different color to change things up. So now I have to use the sine. Oh, one other thing I could have used, and I'm so used to it. So you know what I'm going to do is I'm going to put, and let me just erase that up. I'm going to change it, and I'm going to say that this is easier. B is to the sine of 40 as, and you can use whatever side and angle you want, as I would use the side that's given because that's probably the most accurate actually. 12 is to the sine of 105. See how you have to move fewer things around? So B is equal to sine of 40 times 12. Make sure that that 12 is on the outside of your sine of 40, divided by sine of 105. And let's calculate what let's see what that is. So you can see that my side B is equivalent to 7.986. So let's write that out. 7 equals 7.986. So now I have found all of my sides and I found all of my angles. And that's a pretty nifty theorem using the law of sines. Okay, so now we're going to look at case 2. When you have two sides and one of those sides has to be the opposite angle. So draw your triangle ABC. You know that this side is 15 because that's opposite angle A. Angle A is 94. Side B is 12. And that's all that we're given. So that's all that we have to work with. Okay, so what I would do then, first we want to find maybe notice that B and the side that's opposite is given. So let's start by finding angle B. So we're going to have to use some inverse trig functions. So I'm going to say that the sine of 94 is equal to 15, and that's equivalent to the sine of B, which is equal to 12. So if I solve for sine of B, that's equal to 12 sine 94 over 15. And we're going to put this into our calculator. So let's move that over, and we have 12. Whoops, no, we have to do the inverse. I should have written that, so let's do. So we're going to say that the sine inverse of, and I'm going to put all that in 12 sine 94, close parentheses, divided by 15, close parentheses. And then I'm going to enter, and I get that B is equal to 52.94 degrees. So sine of inverse of all of this, just so remember, if you're ever trying to find an angle, you're going to use the inverse function. If you're trying to find a sine, you're just using a side, you're trying to find the regular sine. And that was, once again, 52.94. So B is equal to 52.94 degrees. Okay, so now we have another angle, which is nice. So we can plug that in 52.94. We can find angle C by going 180 degrees minus 94 minus 52.94, which is 33.06 degrees. So we've got that angle as well, 33.06 degrees, like so. Okay, so the other connection now, we have two of the sides still. We still have to find little c. So we're going to just do that. We can say c is to sine of 33.06 as, and I would use a side that's already given just for accuracy. 15 is to sine of 94. So if you calculate this, let's just do it. We are going to take 15, and I'm going to multiply that times sine of 33.06, close those parentheses, divided by sine of 94, and that's going to give me 8.2. So 8 point, oh, what was it? 02. Let me double check. 8.20. Okay, so now we found all the sides and all the angles. And those are the two cases, and that's what you guys have to do for numbers 1, 3, 5, 7, and 9. Now, I don't want you to get bogged down by the you have an ambiguous case, and I'm not even going to cover that. It's just too technical in this class, and we're just going to skip it. You can read through it. It's important to think about if you ever get into engineering and more applications, but for now we're just going to cover the basic law of sines. So we might cover it later, but for now, like I said, just consider the first angle that you find and use that. Okay, so you're just going to get one answer for when you're solving each triangle. Okay, so this is one of your problems, and the reason why I'm going to point it out is I did this without using law of sines. So, um, if you can, I'm just going to quickly show you and draw a diagram. I use two right triangles, but I still think it's a very good problem. So what I did was I said, okay, here's one triangle, and I think it's good like connection with what we're doing. So here's 30 degrees. This length is 6,000, and I'm going to call this side X. And now I'm going to draw the smaller triangle, and this is 55 degrees. This is 6,000 still. Whoops, which I should draw it to scale so you can see. And I'm going to call this side Y. Now, my hint to you is in order to figure out the speed that the plane is going, you need to find this distance right here. Okay, so this distance is going to be x minus y. So use right triangle trigonometry to find the x and y, and then calculate what that distance is. Now, you're going to be in feet when you calculate that distance. Do you remember how to convert into miles? Well, they say whatever feet you get, and let's just practice. So if you have something like 7,000 feet, for instance, well, an equivalent ratio, something that I can multiply by 1, I know that there is 1 mile, and they say this is equivalent to 5,280 feet. So I just canceled out my units, and 7,000 over 5,280 is going to give you miles. Okay, whenever you divide that. You also are dealing with 10 seconds here, and we're talking about miles per hour, right? So once you find your miles, you put that number on the top. Now you need to convert seconds into hours, and I just thought it's a good practice. So how many seconds in a minute? Well, you can say that 1 minute is equivalent to 60 seconds, right? So boom, boom, cancel those out. And then I can take that one step farther and I can say that 1 hour is equivalent to 60 minutes. Okay, so that's how you convert your units to the appropriate. You've got 10 hours now, 10 divided by basically 3,600. So you can see that. And that should help you with this problem to find the answer. And number 15 is also an assigned problem. You have to draw a parallelogram, and since we haven't seen a parallelogram, I wanted to set it up for you guys. So one diagonal of a parallelogram, it doesn't matter what diagonal you use, is 17 centimeters long. So here's 17, the diagonal, I'm just going to call it this. Okay, and then it says that the angles, and it makes angles 36 and 15. So you can say then that this is 36 degrees, this is 15 degrees. Okay, basically then they want you to find the lengths of each of the sides. So you're going to use the law of sines to find this side, and you can call it whatever you want, A, and this side, B. Okay, you're given two angles in this triangle and one side, and you need to find these two sides. So it's a short lesson because I'm skipping the ambiguity of the case 2 and just calculate those. And then the extra bonus is to play around with the law of sines by drawing a circle and using basically a protractor and measuring. I thought that that would be fun, and I'll give you an extra point if you work on number 10 and show me your artistic side of things. Okay, so this is due Sunday. Have a great week. Set up, start a Q&A if you guys have any questions on the problems. Like I said, I'm okay with you posting any of these on the Q&A forum. Okay, bye.